think I've got 3 things to start with. So first, I guess, thank you so much for the invitation to speak. It's an absolute pleasure. Thanks generally to these Simons folks. These collaborations have been really exciting, especially for a postdoc. It's been so nice to meet so many people and learn so much. In particular, like this work that I'll tell you about sort of came about because of these collaborations. We thought a lot about these real Seiberg-Witten equations in Stanford at a Simons event last year. So this has just been really amazing, and I'm really grateful. That's the first thing. The second thing I just want to get out of the way. I keep having people ask me, oh, this is real Heegaard Floer homology? And I'm like, no. This is not a slight in any way. This is, our R and C real. So that's very important. And the last thing of everything I say will be joint work with Ciprian Manolescu. All right. So let me tell you the very rough outline of the talk. Oh, sorry. The third thing was, maybe the fourth thing. Which colors of chalk are visible? White works. Blue is bad. Sad. Okay. Yellow is good. Okay. But it looks like white. Okay. So I'll keep the question mark here. And red. Okay. I need 2 colors, so you'll have to be a little bit flexible with me. Okay. Great. So there's the eraser. So first, I'll tell you, try and motivate this gadget I want to tell you about today. So some motivation from Seiberg-Witten theory and some really cool, neat applications from the last couple of years. So that'll be sort of the first part of the talk, and the second I'll sort of tell you what sort of the Heegaard Floer analog should be. That's it. Okay. So let me start here by telling you some things you know. So I'm interested in 3 and 4 manifolds, as many of us are. So today, some key players will be some 4 manifold X, which comes with a spin C structure. And of course, there are these sort of amazing Seiberg-Witten invariants, which is some integer associated to this pair. And this is a smooth invariant. It's really good at detecting exotic behavior, extremely powerful and interesting, and sort of, roughly it sort of counts solutions to the Seiberg-Witten equations. Great. There's a 3-manifold version where I have some 3-manifold Y, also with a spin C structure. And in this case, rather than an integer, I get some group HMR of YS, defined by Kronheimer and Rufka, of course. Yes, thank you. Yeah, so the HMs, the HMRs, the HFs, and the HFRs, I'll do my best, but keep correcting me. Yeah, so these are the monopole Floer homology groups. Right, and these sort of satisfy some TQFT properties, so in particular cobordisms, sort of give you linear or maps between your monopole Floer homology groups. Okay. There's sort of been a lot of interest lately in sort of adding an additional piece of data to these objects that we're studying. So I'm now going to cheat. So I'll add to this data some involution tau. So squares to the identity. And I would sort of like to cook up some gauge theoretic invariant that sort of takes this symmetry into account. So in the Seiberg-Witten world, the idea is, so I've got this involution x, and I'd sort of like to pick a lift of this involution to the spinor bundle. And it turns out sort of the interesting thing to do is to pick sort of an anti-complex linear lift. And this sort of, if you pick this to be compatible with Clifford multiplication, this gives you sort of some symmetry on the space of solutions to the Seiberg-Witten equations. And you can sort of count the solutions which are sort of invariant under this action. So it counts sort of invariant solutions. I know this is I'm not supposed to do this on the board, so forgive me. And great, this has sort of been around for a number of years, developed by some folks such as Tian-Wang, Nakamura, Konno-Miyazawa, and others. I can do the same thing at the 3-manifold level. I can equip my 3-manifold with some involution as well, which I'll also call tau. And here I'll add my R back in, and I get some sort of real monopole Floer homology groups that take this involution that's sort of compatible with my spin-seq structure into account. And again, this has been studied by a handful of folks, but in particular, Lee, as well as Konno-Miyazawa-Taniguchi. Great. Now, even if you don't care sort of intrinsically about involutions, these are sort of interesting because they give you invariants of knots and links and surfaces in S3 and S4 in sort of an obvious way. If I have, let's say, some surface embedded in S4, I can, of course, look at its branch double cover. C over S4, and this comes with an involution, of course, and I can sort of define what I'll call, the degree of this embedding of this S2, and this is just the real Seiberg-Witten invariant of the branch double cover of this surface. Okay, some positive integer. Okay. In this talk, this was sort of studied in this paper of Miyazawa, so I will call this the Miyazawa invariant. And of course, there's sort of an analog for links, which I'll just write for completeness here. I've got some link in S3. Of course, I can also consider its branch double cover, which comes with an involution. And I'd like to sort of extract some integer invariant, so I'll define the degree of my link L to be the Euler characteristic of this HMR of the branch double cover of L. I guess I should take some absolute values so I don't have to worry about signs. And again, this is some positive integer. Okay. So I've not really said anything yet, but any questions before I move to the next step? I'm not going to worry about it, but yeah. Other things?
Can I ask a stupid question? What is real about considering an illusion?
I'm sort of, somehow you should sort of think of this as being sort of complex conjugation. I'm interested in sort of the invariant part being like the real part. Other questions? Sorry, yeah, go on. You can do whatever you'd like. I guess here I mean maybe the hat version to just to extract this number. That's a great question, and I don't know. It seems sort of a weird invariant, as I'll try and convince you now. All right, so this is the structure of these invariants. And there have been some sort of remarkable applications in the last couple of years. The first one I'd like to emphasize is this theorem of Miyazawa. And he proves that there exists some embedding of RP2 into S4, which is topologically standard, but not smoothly. And he does this by using this invariant here. And it's sort of, because it's sort of a nice argument. Let me sketch roughly how this goes. The first sort of question is, if I want to study, I don't know, knotting in S4, what are interesting ways to cook up knotted surfaces? So there's this construction called sort of spinning or roll spinning. And the idea is roughly, I'm going to fix some knot in S3. I'm going to use this to cook up some interesting embedding of S2 into S4. So I'm an excellent artist. You'll be amazed by these drawings. So very roughly what I'm going to do is I'm going to pick some knot K. I'm going to say maybe puncture in S3, and then I'll sort of wrap this arc through S4 until it sweeps out sort of the canonical slice disk for K connects its mirror. And maybe so I've got some slice disk for K connects its mirror. I'll maybe compose with the trace of just some constant isotopy, and then I can cap off this disk with sort of, again, this canonical slice disk for K connects its mirror at the top. So this is like the spun 2-knot associated to this knot K. Turns out there's something sort of interesting you can do in the middle. So I have sort of these two canonical slice disks in the top and the bottom, and there was this middle section where I didn't do anything. Instead, what you could do is you could take sort of one copy of K and sort of drag it around longitudinally through the knot. So it'll look something like this. So I take this sum in and I drag it through K and eventually back to itself, and then I cap this whole thing off with my canonical slice disk for K connects on its mirror. And this thing here, I'll give a name. I'll call this rho of K. This is like the roll spun knot for K. That is really beautiful. Great. So Miyazawa's construction is sort of really simple. So you pick a particular knot in S3. So you look at the -2, 3, 7 pretzel knot, which again looks something like this. And you apply this roll spinning construction to this knot here. And you can check that the fundamental group, I'm supposed to cook up some RP2s, and I've been telling you about embeddings of S2. So the point is I'll take P0 to be sort of the standard RP2 in S4, and then I'll sort of compare it to P0 connect sum, this roll spun thing here. So it turns out, and this is not so bad, the fundamental group of the complement of the standard RP2 is Z mod 2. And it turns out this is the same as the fundamental group of the complement of RP2 when I connect sum on this 2-knot. Okay. And there's this remarkable theorem of Conway, Orson, Powell, which tells you that this actually implies that these two RP2 knots are equivalent topologically. So I'll say S4 P0 is the same topologically as S4 with this P0 connects some rho of k. So you, of course, would like to distinguish these smoothly. And I don't know, if you'd asked me a couple of years ago, I'd have said, well, good luck. I mean, this is like upstairs, you've got something that's homotopy equivalent to CP2 bar. Like, what invariants do you have? But it turns out you can use this degree invariant. So to make this really symmetric, let me say something like the following. So I'd like to compute this degree of the standard RP2 connects some rho of k. And I'll compare this to the standard RP2, but I'll write this as standard RP2 connects some the roll spun of the unknot, which is just the standard S2. So this degree, it's sort of multiplicative. So this will be the degree of P0 times the degree of this roll spun thing. Turns out the degree of the standard RP2 is 1. So this is just the degree of these roll spun two knots. And you could sort of simplify this further. It turns out this is actually just the same as the degree of this knot k. So it doesn't actually, it's just some, well, what should I say? This really just depends on the Euler characteristic of the Floer homology of the branch double, the real Floer homology of the branch double cover of this knot k. And the same thing here. And the thing that's sort of bizarre is, of course, the Euler characteristic in this case is 1. And you just sort of expect this one to be as well, but it turns out it's 3. And so you have this smooth obstruction, it turns out. Of course, these are not equal. So you have this sort of exotic copy of RP2 and S4. Weird, I don't know. Let me pause here, because anything I can say. Great. I'm good at saying nothing. But I'll keep talking for another half hour, sorry. All right. The other application that I'd like to highlight that's quite cool that uses these real invariants is this work of Park. Sorry, let me get the Kong, Park, Taniguchi. And we heard about this earlier today, but they use these real invariants to prove that let me get this right, 4n plus 2 comma 1 cables of the figure 8 are not slice. And again, these were sort of known not to be ribbon, so this was some chance of attacking the slice ribbon conjecture, but it turns out these are not slice. So the thing that, I don't know, gets me sort of excited about this perspective, not just, I mean, these are great results, but the other thing that really excites me is the thing that really actually distinguishes these RP2s is the fact that you could distinguish actually the spheres. So there's sort of the natural question, is can this degree invariant detect sort of exotic S2s and S4? Obviously, it can distinguish these, but these are topologically distinct. That's sort of not so hard. But it's sort of hard to write down examples of candidates of exotic S2s whose invariant you can compute. So the idea is, well, maybe you should try and define a Heegaard Floer version of this, which should be more computable, which is what I'll try and tell you about. So I'll give you the same sort of empty spiel about the structure of these Heegaard Floer invariants. I'll say a little bit more. So the structure is, of course, very similar to in the case of monopole Floer homology. Here I'll just think about the 3 manifolds. I've got some 3 manifold with a spin C structure, and again, I associate to it some abelian group, HF of Y, and the spin C structure, of course, defined by Schwaff and Szabo. And again, these are sort of functorial. with respect to cobordisms. And we know the Heegaard Floer groups and the monopole Floer groups are the same. But sometimes it's easier to do concrete computations on the Heegaard Floer side. So I'll say just a word about how these complexes are defined. The idea is you take your three-manifold Y, and you write it as the union of two handle bodies glued along some surface sigma, like this. And now there are colors. And this is going to be really hard because alphas are red and betas are blue, but I only have a yellow. So great. I can sort of record the data of the splitting by specifying a handle decomposition of these two handle bodies. And the way I do that is I sort of tell you what the co-cores of the disks down here look like and the cores up here. And these just give you some collections of curves sitting inside the surface. So, oh boy. In red, I've got alpha 1 through alpha g curves. Like that. And then I've got some collection of beta curves, beta 1 through beta g. And then the idea is from this data, we would like to cook up some invariant. And the idea is you should look at the g-fold symmetric product of this surface sigma, where all these curves we're living in. And you sort of note there are two nice half-dimensional submanifolds that live in here. T alpha, which is the product of all the alpha curves, and T beta, which is the product of all these beta curves. And you can equip this with a symplectic form, which, with respect to which these are Lagrangians, and you sort of define the Heegaard Floer homology of Y to be just the Lagrangian Floer homology of T alpha and T beta. And then you notice you made all these choices in the definition of this invariant, and then you prove that it doesn't depend ultimately. So, of course, you'd like to do the same thing, but now in the situation where there's some symmetry. And so what you'd like to do is you'd like to pick your splitting. Sorry, now I've got Y with some involution tau. And I'd like to split Y into, again, two handle bodies in some way that sort of respects this involution. And the way I'll do that is I'll ask that if I apply tau to the alpha torus, this is the alpha handle body, this is the beta handle body. So in particular, if I restrict tau to my surface, I get some orientation reversing involution of the Heegaard splitting. Okay. Great. And so in the same way as before, if I have some symmetric Heegaard splitting, again, I can pick some alpha and beta curves. And the point is, if I pick some alpha curves like this, there's some involution on this surface, which I'll also just call tau. And this determines what the beta curves should be, since these two handle bodies get exchanged. So here I'm thinking about my involution as just being reflection. So I end up with one beta curve here and another here. And I get these sort of symmetric looking Heegaard diagrams. You can always find a decomposition like this. They're not so hard to build, but yeah, I should say this. So this does show up in the literature. There's an old paper of Nagase where he considered these real Heegaard decompositions. He calls them characteristic, but we're trying to imitate this real monopole Floer invariant, so we call these real Heegaard splittings, and they exist. And there's some collection of moves between equivalent ones. Well, there are collections of moves that relate diagrams for the same underlying manifold with involution. And I'll say a little bit about this at some point. Other things? It exchanges the handle bodies, and I'm sort of abusing notation, and I'm looking at the restriction of tau to the surface here. So maybe let me say just a couple words about sort of what's the general situation we sort of find ourselves in. The point is here we've got some symplectic manifold which comes with an anti-symplectic involution. Okay. I guess it's not so hard to see that if I have this involution on the surface here, that gives me an involution on sim G. And it's anti-symplectic. And let's say now just have a single Lagrangian living in here. One thing you could do is you could sort of think about this chain complex, which I'll call CFR of L, which is sort of generated by points in the intersection between L and its image under this involution R. And I want to look at those points that are themselves fixed. And then I want to define some differential that sort of roughly counts sort of symmetric strips. So, the thing you sort of expect. I'm going to sum over all y, count holomorphic strips, and see if I can get these colors right. Into M. So that this part of the strip gets sent to L, and the other part gets sent to R of L. And I have this obvious symmetry of the strip, and I want that to sort of interchange the symmetry I have in M. What should I say here? Such that I want to count J holomorphic strips. And the thing I guess I'll emphasize is I sort of want to choose symmetric, almost complex structures. So that, JT composed with the involution is minus the involution composed with J of 1 minus T. Great. So in our setting, here's the situation. So M from now on is going to be sim G of sigma. And I get this involution on sigma coming from this involution tau on the surface. And I'm going to define HFR to be the homology of this complex up here. So HFR of just T alpha. Sort of T beta is sort of determined by the involution. So maybe let me give you a silly example. So again, I'll think of my involution as just being reflection on the surface, and I need to draw some symmetric collection of alpha curves. Okay. So the points in sim G are sort of unordered tuples of intersections between the curves, and I just want invariant ones. So here's an example of a generator here. So I'm in sim 3, so I need 3 points, and I can pick these 3 points here. These two get swapped, and this one is fixed by the involution, but I'm only looking at unordered pairs. So this triple is sent to itself under the action of R. And I'd like to show you some domains, because the thing that sort of makes this interesting is, there are other sort of versions of Heegaard Floer homology that incorporate some symmetry. But the point is you sort of look at the symmetry on sort of the old complex. But the point is here we're actually going to count sort of different curves. And so it's really a different complex altogether. So let me show you some things that will show up in the differential. So we can sort of see a picture of this. So in white, I'll try and draw the fixed set on the surface. And for simplicity, the involution will always just be reflection. So here's a symmetric pair of curves. Okay. And I'm looking for bigons in this picture. So there's, of course, an obvious one here from x to y. There's a bigon like this. And this is clearly sort of a symmetric term. So this will show up appears in the boundary of x. Let me maybe say a word about this, but here there's a zero-dimensional moduli space, both in the real and the ordinary setting. Right? There's this sort of R action I can translate, but that translation is sort of symmetric. So the index of this class phi is 1 in the usual case and also in the real case here. So these show up in both the real complex and also the ordinary one, but that's not always the case. So here's another sort of silly example. I could just look at pairs of bigons. Okay, that gets swapped here. Okay, so now I'm in sim 2, and I can look at sort of the pair of these disks as a single class phi. And in the usual case, the index is 2. I can sort of translate in either disk. So this would not show up as a term in the differential, because I've got sort of a one-dimensional moduli space. But I don't have 2 parameters in the real case, because sort of the translations and both the 2 disks have to agree. So the real index is 1 in this case, and this domain will contribute to the differential here. Sorry, yeah.
How do you make sure these moduli spaces are transversely cut out?
It's basically a modification of the usual transversality argument, it turns out. Yeah. I'm happy to chat maybe more about that later. Other things.
Do you know how this compares? I mean, you can look at the action on the chain complex by tau, and like you can use that to build sort of like a covariant, complex, if you like. I mean, maybe this requires kind of infinite order naturality in order to really get the full thing. But like, would you expect that the sort of spectral sequence there is related to this invariant?
I imagine there is some spectral sequence. Let me say something intelligent here. There are all sorts of fancy tools. I guess the naive thing to slightly worry about is, maybe I'll give you an example right now. You can't always achieve transversality simultaneously for sort of the things that appear in CFR and CF. So I'll maybe try and convince you of that right now. Yeah. Yes.
Chef Plus?
Yeah, it's, what should I say? It's sort of the thing you sort of expect in link Floer homology, like there are, if you have extra base points, there's curvature, but it's sort of also hard to track down what it is. And so, yes. I don't know.
Okay.
Yes, yeah. And there's some choice about where the base point goes. It should be on the fixed set, but if I've got multiple components, there's some choice. Yeah, other things? Sorry, forgive me for belaboring this point, but let me show you just two more sort of interesting examples of domains. So here's some domain, and the index in the usual case is 2, because there's sort of this one parameter family of cuts I can make here. But again, those aren't symmetric, so the real index is 1. And the sort of last most interesting example, I mean, you sort of might guess that the index is always, that this is always at least smaller, but that's not always the case. So let me give you one more example. So here's some class in Sim2. So disks into the symmetric product. I'm supposed to think of branch double covers of the disks into the surface. So the annulus will double cover the disk. And you can ask if that will have a holomorphic representative. And that will depend on sort of the ratios of the alphas and betas on the inside and outside of this annulus. And so for a generic, almost complex structure, the point is that ratio will not be right, so you won't get any holomorphic representatives. But if you insist that this is symmetric, for a generic sort of symmetric, almost complex structure, there is a representative here. All right, so this is sort of an interesting example. What else am I supposed to say? So the last thing I'll sort of say here, and you can sort of see it really clearly in this example. Another perspective is, well, if I have a sort of a symmetric disk, I can sort of restrict to 1/2 of this strip. And what you see is sort of a symmetric disk is sort of the same thing as a disk between T alpha and just the fixed set. So you could sort of compare HFR of T alpha, as I've written it, to just the usual Floer homology of T alpha with the fixed set of this involution. And if I work with sort of these symmetric, almost complex structures, it's not so hard to see. You can sort of identify the two moduli spaces. So we actually just sort of define the real Floer homology to be this, but we sort of visualize these disks between T alpha and the fixed set as sort of these symmetric disks. You actually can see them in the Heegaard diagram. And so maybe philosophically somehow, maybe this makes you feel a little bit better. Somehow this is just like the usual Floer homology of T alpha and just some slightly weirder Lagrangian. And maybe I'll remark, like, what is the fixed set of this involution in Sim G? And it's too bad. I mean, it sort of looks like tuples of the form some point Z and its image under the involution. And I have some number of these. And then I might have some number of points on the fixed set, which I'll call C, G minus 2R. So it's not so hard to see, like this sort of has a nice stratification at least as Sim R of the quotient of sigma across Sim 2G minus R of the fixed set, which I'll call C. Yeah.
On the top board there in the middle, where there's bygons, which don't meet the fixed point set in the middle. Is that, I'm having trouble interpreting that as something between the red and the fixed point set.
Yes. And this is why these are sort of hard to visualize. I think the point is you can see the fixed set of sigma very clearly in this picture, but there are all these other sort of facets of
Oh, there's fixed point set in
yes, in the symmetric product.
Yeah, right.
Yeah.
Got it.
Yeah. Sort of, yeah, the symmetric picture is a lot nicer. But let me say something else here. Right, so let me say something. So this is really an invariant. So H F R Y tau is an invariant up to isomorphism. And you basically do exactly the thing you expect. You have this list of moves that will relate any two real diagrams for the same three-manifold involution pair. So they're sort of, we call these real isotopies, where you move the alphas and betas simultaneously. If you do a handle slide, again, you slide alphas and betas at the same time. And then maybe the thing that's slightly more interesting is there are real stabilizations. And it's probably not too surprising, but there's sort of now two different kinds of stabilizations. You can sort of do stabilizations in pairs away from the fixed set. Oh boy. So I've got sort of birth-death index 1 and 2 critical points appearing in pairs. But I could also see sort of an index 1 and 2 critical point appear on the fixed set, in which case there's sort of a move that looks like you sort of attach a handle on either side of the fixed set like this. Boy. I definitely didn't draw that right, sorry, but something like this. And you check that these moves give you chain homotopy equivalences between the various complexes to get invariants. Yes, as E mod 2 right now. Yeah.
I'm sure I missed this, but why are the real isotopes in this in quotes in the real?
Oh, somehow I guess what I really mean is like I guess I'm putting real scarecrows on the real because I haven't really defined this. It's the thing you would sort of guess if I tag on this adjective. So presumably this invariant is natural, which is a scary thought, but we hope to work that out. And once naturality is sorted out, there should be invariants of 4 manifolds as well. But maybe in the time that's remaining, let me specialize to knots in S3 and try to relate these invariants to this degree invariant of Miyazawa. Sorry. Let me just say, for knots in S3, it's pretty easy to write down explicit real Heegaard diagrams. You sort of, if you apply Seifert's algorithm to your knot, you'll get a Seifert surface for this knot whose complement is a handle body. So if you sort of thicken up this Seifert surface and cut it out and then glue 2 copies of the complement together, it's not so hard to see that will be a real Heegaard diagram for the branch double cover of K. So I'm going to skip that. But then the thing, of course, you would guess is that whatever the Heegaard Floer analog of this invariant is it should be computable easily. And that's true. So I'll write HF for the Heegaard Floer analog. And again, this is just the absolute value of the Euler characteristic of HF R Y tau. And I've remembered the spin C structure. Sorry, I've forgotten. What have I done? Right, which is some positive number. And the point is, this is computable algorithmically from a Heegaard diagram. And that's why this perspective is sort of nice. Because if I'm just looking at the Lagrangian Floer homology of these two Lagrangians, the Euler characteristic should just be the algebraic intersection pairing of these two Lagrangians. And maybe it's believable that you can read that off from the Heegaard diagram. That's what we do. Sorry, a real Heegaard diagram, yes. Yes, from a real Heegaard diagram, thank you. Thanks. Any more gaffes?
So you have the same, I mean, you also have the Heegaard diagram not viewing it as real, in which case the Euler characteristic determine that the relative indices are shifted around now in some weird way.
Yeah.
And you expect it's like related to like some twisted Alexander polynomial
I have no idea what it's
evaluation.
related to, but I would love to hear any suggestions. I'll like, algorithmic. Okay, a computer can do this, of course. So let me give you some examples of these. And again, they're just sort of weird. Right, so for small knots, I'll just note small crossing knots. Sorry. These real Heegaard Floer groups, of course, split over sort of real spin C structures. So you could ask about the Euler characteristic in every spin C structure. And so really what I mean here is this Euler characteristic, HFR of Y tau. Sorry, and I guess I should really have written the branch double cover of K tau here. I am going to sum over all spin C structures. And please forgive me for writing chi S of K for the Euler characteristic of the branch double cover of K in real spin C structure. Okay, and there's some sign ambiguity here that you can sort of fix by, say, I want to make sure that the total sum is positive, and if you do that, that sort of determines the sign on the individual terms. But let me give you some examples. So if I look at this total Euler characteristic, say for 3, 1, it looks like this, sort of in the central spin C structure, the Euler characteristic is -1, and for the outer ones, it's 1. And again, this is sort of odd because the total, chi S is this tuple, and so the total Euler characteristic is 1, which is, of course, not the determinant of 3, 1, which is a little bit odd. The other thing that's a little bit weird is in the usual Heegaard Floer context, the Euler characteristic is independent of the spin C structure. And somehow the point is you can sort of drag the base pointer out on the diagram, but you're not allowed to do that in this case. You sort of have to stay on the fixed set. So you don't have as much freedom. The other thing is, for larger knots, this Euler characteristic isn't always just plus or minus 1. So there are some knots here, K, which are like 11 or 10 crossings, 10 or 11 crossings. Again, where this degree is plus or minus 3. And so particular, if you take this example from Miyazawa, this pretzel knot, we again compute this Euler characteristic as 3 in the unique spin C structure. And I'm 49 seconds short, but I'm going to stop there.